Okay, I'm happy to report that I think we're back live on air, right? Yeah, okay. So welcome to the worldwide audience. It's a pleasure today to welcome Simeon Philippe from Harvard, who's going to tell us about Hodge theory and applications in Teichmuller dynamics.
All right, so thank you so much for the invitation. It's a pleasure to be here. So I'll talk about what the title says, but as a motivation, I want to start with some examples for which would hopefully explain why people care about the kind of questions that I'll be discussing. So one simple example that goes back a long time, so this is called the Ehrenfest-Wintry model, is the following. So it's just an example of a dynamical system where you take a bunch of rectangular barriers, which are arranged in a Z2 periodic fashion. So and what you can consider is the motion of a billiard ball in this space. So maybe it goes like this, and then it bounces, and then it hits some other box here. Then it comes back, and then comes back somewhere else, and then, so this, if it bounced correctly, these two lines should be parallel. My drawing is maybe not so good, but you hopefully get the idea about how this dynamical picture looks like. And one question you can ask is, for example, how does this trajectory diffuse if you send it at some random angle? So let's say that you start at angle theta, and you can ask, what is the typical distance if you flow for time t in the direction theta for this starting point x? And if you would think that this behaves anything like Brownian motion, then you would expect that this diverges roughly at exponent t to the 1/2. So that's a typical diffusion rate. But what turns out to be the case is that, so if you normalize it like this, and then you take the lim sup as t goes to infinity, then this actually approaches 2/3. So this is what happens. And so maybe I should attribute this. So a number of people worked on this model. So Delacroix, Hubert, Lievre, and Trubetskoy. And so maybe I'm not naming all the people, and there's all sorts of questions that one can answer about the system. So what's amusing here is the fact that this number turns out to be rational, and this rationality goes back to the following sort of more general question that was asked by Anton Zurich, and even before this, so there's something called the Novikov problem. So suppose that you have a foliation on a surface. It looks something like this. So you have a foliation like this. So you can think of, I'll explain in a few minutes how to get from a picture like this to a foliation on a surface. And if you take gamma t, okay, so let's see, gamma t is a long leaf of this foliation. So then you can close it up, and you can take a class in the homology of this surface. So you close it up in some way. So your leaf is going around for a long time, and it might start here and end here. So maybe it went in like this, did stuff, and then came back. You close it up in some way. It doesn't really matter which way you close it up. You make some bounded error. So for the kind of questions that I'll be discussing, this is not going to matter. So you close it up in some reasonable way. And then you ask, what is this homology class? How does it look like asymptotically? And it turns out that there's a main term. So this is approximately equal to t to the times C1, where C1 is some homology class, which really you can compute from looking at this foliation. So you can associate the homology class to it. But what turned out, so this was first discovered by Zurich experimentally, was that on a computer, meaning So there's a next order term. So if you subtract this from this class, you get the next order asymptotic. And it keeps going up until the genus. And then there is a bounded error. So you have these numbers, 1, lambda 2, up to lambda g. And so the fact that here you have a strict inequality sign, this is a theorem of Forney. But the next exponents could a priori be equal. In fact, in the general case, it's known that they're not. But having this structure, this asymptotic expansion was a little surprising at first. But what was even more surprising was the fact that the sum of these numbers was a rational number. So if you forget about the fact that the first one is lambda 1, and it's 1, lambda 2, and then the other ones don't have a priori, at least from what people have computed numerically, they don't seem to have any particular structure, but their sum seems to be rational. And I'll try to explain at least a little bit how, maybe by the end of the talk, how this is related to Hodge theory. So it turns out that this sum, it's not just known to be a rational number. There's a formula for it in terms of degrees of some line bundles over some spaces. But first I have to talk about those spaces. So these will be moduli spaces of, depending on how you want to see them, either surfaces equipped with, there'll be surfaces equipped with some kind of geometric structure. So the moduli space is going to be the following. So we're going to have, so there's a combinatorial description. So H alpha is surfaces glued out of polygons. So I'm trying to describe it in this kind of informal way, but I'll hopefully by example it'll be clear what I mean. So the surface is glued from polygons by translations. So you're not allowing any kind of gluing, but one will be with translations, and with some singularities allowed. So this alpha is alpha 1 through alpha k, which will describe the kind of singularities which you allow. So going back to this picture, I said I'll promise how to explain how to get a surface from, like on the second board, from this picture. And to get a surface, you can take a fundamental domain for the picture over here. So here's an example. So if you take the fundamental domain, you will see something that looks like this. So you have this L-shaped polygon. And how do you glue it? So I said that it's a surface glued out of these polygons. So here you have just one polygon, but you have to specify how to glue these edges. So what you do is you glue the top to the bottom. So imagine that you've translated this polygon above, and you've glued it so that here you have something that, this part lives over here. And then similarly, this side is identified with this side with this side, and then this one with this one. And then I also said that there are some singularities which are allowed. So the singularities are obtained by, will live in this case at this point. So in the glued surface, this is a single point. And what kind of singularity do you have? Well, so in some sense, it's a two-sheeted singularity. So if you imagine two sheets of paper, so imagine that this thing lives on a sheet of paper. So around this point, if you unfold everything appropriately, you'll get really not a single sheet, but rather something that locally has this picture where you have this top side, which if you move over here, you come out on the bottom side on the other side. So you go this way, come out this way, and if you go around this loop, you come out at the bottom here, and then you come out in a loop. Okay, so you allow this kind of singularity, and so you'll see that you have a flat metric here. So you have a flat metric with cone angle yeah, so I guess here I think here you should actually get 6 pi. So strictly speaking, here you should have a third one, and you should do it in a cyclic order. So here, here this is cone angle 4 pi. But for this example, you'll get a cone angle of size 6 pi. So you should add a third sheet and glue them in cyclic order. So sorry, I just realized that. So this is a slightly degenerate example. The cone angle 4 pi is more generic than the 6 pi one. So for genus 2, you would have either 2 such cone angle 4 pi's or 1 cone angle 6 pi. OK, so this is the combinatorial description. Now, the thing that's useful about this space is that it also has a different description. So you can also think of this space H alpha as pairs x omega, where x is a Riemann surface, and omega is a holomorphic one form. And so how do you get such a picture? So let's say that somebody gives you a polygon. How do you go to a Riemann surface? Well, what you do is, in this picture, you have, imagine, so the polygon lives in R2, which you identify with the complex numbers. And the one form omega is just dz, and it will descend. So it will descend for these gluings, because the gluings are of the form, so the gluings are of the form z goes to z plus some constant. And dz is invariant by these kinds of translations. So this Riemann, so this one form, omega equals dz, descends to the glued surface. And in particular, it gives you a structure of Riemann surface on this glued surface. So can I write here? Can everybody see here? OK. So to go the other way, so to go from x omega to the polygon, so there's no kind of canonical way, but what you can do is you can triangulate your surface using the zeros of omega, and then you just obtain polygons. So you cut it into polygons. So why is it that you get polygons? Well, the point is that a holomorphic one form, so away from zeros of omega, this holomorphic one form looks in omega is the one form. In the right coordinates, so away from the zeros of omega, there exist coordinates such that omega is just equal to dz. And so you can choose these kinds of coordinates to obtain this polygonal structure on the cut-up surface. Of course, so one thing that I forgot to mention was that the zeros of omega correspond to the cone angle, the points with higher cone angle. So under this correspondence, so zeros of omega correspond to the cone angle singularities. OK, so this is the space. So now I have to tell you coordinates on the space. So the coordinates. So the coordinates, the standard coordinates that people use are as follows. So they're given by this combinatorial description, and they come from so it's some c to the n, which is the sides of the polygons. with appropriate relations imposed. So for example, if you have this polygonal decomposition, you just remember all the sides of the polygons. And so in this case, you'd have some parameters. You'd have this side. You could think of this as just Z1, Z2, Z3, and Z4. And in this case, you might try to see if you perturb them a little bit, you'll get in the complex plane, you'll still get a polygon that closes up, and you glue them according to that rule. In general, if you have some more complicated polygonal decomposition, you might need to impose some extra relations, like some segments have to sum up to 0 or things of that nature. So this is what I mean by relations imposed. But more canonically, so without talking about a specific polygonal decomposition, this is just the following cohomology group. So Z omega C. So what's Z omega? This is the zeros of omega. And what is this cohomology group? So this is this is something, this cohomology group, if you draw a path on your surface which has its boundary, so if gamma is a path on X such that the boundary of gamma is contained in the zeros of omega, then you can just take the integral over gamma of omega. So this is a complex number. So you integrate this one form, and it gives you a complex number, which is the corresponding segment. But some of these paths will correspond to genuine segments in some triangulation, others might not. But this is kind of the canonical way to describe these coordinates. So one thing that I should emphasize is that these coordinates are not. So we had these two descriptions of the moduli space. One is this combinatorial description, and the other one is this description as Riemann surfaces with a holomorphic one form. And this, in this description, this is a quasi-projective variety, meaning that there is some. So if you think of the moduli space of Riemann surfaces, that has some structure of algebraic variety. Of course, it has other more, perhaps more useful descriptions for people who do geometry, like moduli space of hyperbolic surfaces. But it also has this algebra geometric description, and then the bundle of holomorphic one forms also has, has this algebraic structure. And so this total space has a structure of an algebraic variety, but it's very different from this description as a moduli space with of combinatorial objects. So these structures are complex analytically, they're isomorphic, but these complex numbers, these charts to Cn, are not the kind of charts where omega, where this variety would be kind of described by some kind of polynomial equations.
So I'm confused about your dictionary. So in your geometric description, you're effectively specifying choices of cone angles.
Yeah.
So are you fixing the multiplicity?
Yeah, I forgot to say this. As I was saying, I realized it, but I didn't want to say it to not confuse. But yes, so zeros of omega have multiplicities alpha 1 through alpha k. Yes, thank you. I forgot to say this, so the zeros should correspond under this. So here, this is not the full moduli space, but it depends on this alpha, which I didn't specify.
And the cone angles are 2 pi times alpha plus 1?
Yeah, so yes, so the angles are, yes, 2 pi. Yeah, so then maybe let me say this. So alpha 1 plus alpha k is 2g minus 2, and the cone angles are 2 pi alpha I plus 1. Yeah. Okay. So this is so we have the space with these two descriptions, and the way it connects with the examples I started talking about at the beginning is via this action of a group. So you have this action of GL to R, which acts on this space H alpha. So how does GL to R act on this space? So you have to look at it in this combinatorial picture. So if you have a polygon, oops. So suppose you start with this polygon, and you have a matrix A, then if you act by this matrix, you'll get a different polygon. Let's see if I can make this parallel. So your matrix A will have two eigenvectors, so maybe it will stretch things quite a lot in some directions, but it will preserve parallelism. So whether two lines are parallel or not is preserved by the action of GL2R. So this preserves the notion of parallel lines, or maybe parallelism. So whether two lines are parallel or not stays the same. And if this segment was equal to this segment, when you apply a matrix to it, this will still be true. Maybe this segment gets longer, but so will this one. So this descends to this gluing. In coordinates, when you have this complex cohomology group, you have this h1, x, z omega, and so complex numbers. But then you just view the complex numbers as R2. So you're just acting on these segments. So you have this complex number, and you think of it as a vector in R2, and you just act by the matrix on this vector. And it is this action. So let me make the following a few remarks. The first one is that it is not a holomorphic action. Meaning that if you take a fixed matrix and you act by this matrix on, you get a self-map of a space from H alpha to itself, this map is not going to be a holomorphic map. However, it has the orbits, these GL2R. So I'm putting the plus so that the orientation is preserved. Orbits GL2R x omega are locally holomorphic submanifolds. Maybe let me put locally here. Local pieces of orbits are locally holomorphic, meaning that, so GL2R is R, locally it's R4, which is C2. So in these coordinates, you can check that what you get if you apply this action, you're actually going to get a small piece of C2 which is embedded, but it's not going to be it's not going to vary somehow holomorphically. So you can think of the picture as the orbit picture as this. So locally, each of these submanifolds, so this lives in Cn, each of these submanifolds is some C2, which sits in here holomorphically, but they don't vary holomorphically in the transverse direction.
Can you say what the orbits through a fixed point of H of alpha are in some algebraic way?
Sorry?
Is there some other algebraic description of what those orbits are?
Yeah, so algebraically you cannot describe a single orbit. So the difficulty is the following. So and this is the next thing that I'll discuss. Namely, an orbit can come back and it comes back as a different leaf, and then it can accumulate, and the orbit is going to be something quite wild in general. So a single orbit, you cannot, at least I don't know of a genuine description in terms of just purely algebraic geometry. Somehow the vector, so you have some vector fields. So GL2R, take the Lie algebra, you have some vector fields. I don't think there's an algebraic description of those vector fields, except for two simple cases. So maybe to continue the remark, just let me say that the C star, which lives inside GL2R as scaling and rotations, so this is not interesting in a sense, because this is just rotating this picture or scaling it. So we normalize area 1, so normalize to area 1, the surfaces. So and the group that acts, people usually consider the group as L2R so that you don't change the area. And so then this action is actually related to the initial dynamical systems that I was talking about. So this space H alpha can be thought of as some kind of moduli space of dynamical systems. And the behavior of a single orbit tells you something about the initial dynamical system. And so that's how the correspondence goes. Okay, so maybe let me write this, and I will not come back, because the passage from in this relationship is itself kind of a separate and complicated story. But the GL2R orbit of x omega controls many aspects of the dynamics on x omega. So by knowing what happens to x omega when you deform it with these matrices, you can figure out what. So there's a way to go back and forth between what the orbit of x omega in this ambient space does to the dynamics on x omega itself, where you never think about any other surface but x omega. So there's this dictionary, but it's kind of a separate story how to go back and forth between these two things. Okay, so that's that's the story, and so the key theorem here is that, so due to Eskin, Mirzakhani, and Mohammadi, is that for any x omega, this GL2R orbit closure, so not the orbit itself, but you have to take the topological closure. So this orbit closure, so the orbit closure is, and so there's no standard name for this, so people call it mostly an affine invariant manifold. So it certainly has an affine structure, but not any affine manifold gives you. So sometimes in differential geometry, affine refers to just any manifold that has charts with transition maps in the affine group of Rn. So these manifolds, so let me call it M. This is this GL2R orbit closure. So going back to the remark here that you look at this orbit closure, and so the content of the theorem is that for any such leaf you get some manifold. So this really depends on the fact that this group is large, and so you could in fact take the upper triangular subgroup, and this would still be true, but it would be absolutely not true if you took, for example, the diagonal subgroup. So somehow this was inspired by theorems in homogeneous settings by Rotner. So this is the statement about this orbit closure, and to go back to the question of whether this is related in some way to the So maybe I should tell you what an affine manifold is. In this setting, so locally it's cut out by real linear equations inside in these coordinates that I described there, these combinatorial coordinates. So thinking in terms of polygons, the kind of real linear conditions you can impose would be maybe that this segment is twice the length of this segment, or maybe this segment is a third this plus 5/3 of this, or equations of this nature. But if you think about them in terms of the underlying Riemann surface, which if you think of it as an algebraic curve, These kinds of coordinates, these kinds of conditions are absolutely transcendental. They don't have anything to do with the polynomial equations that would cut out, for example, that algebraic curve. And then the theorem is that, in fact, you can describe these affine manifolds using just purely algebraic geometry. So these affine manifolds, so I'm just going to call them affine invariant manifolds to kind of make sure that they're distinct. They're the affine manifolds which occur in this context, not just any affine manifold. So these affine invariant manifolds M are, first of all, they're themselves quasi-projective varieties. So in this algebra geometric setting, there's a way to describe them algebraically, and they're characterized by some conditions. So anytime you find some variety which satisfies these conditions, then it occurs as one of these affine manifolds. So the first condition is that, so I'm going to be a little vague about the conditions because if you haven't, because they're a little sort of technical to state, and they might not be so familiar. So the first condition is that the Jacobians of these x parameterized by M, they have extra endomorphisms. So if you don't know what the Jacobian of a Riemann surface is, I'll explain this in a minute. So the typical case is something called real multiplication. So the second condition is that there are certain, so the points, so the zeros of omega, they satisfy certain torsion relations on the Jacobian, on maybe, let me say, a factor of the Jacobian. So I'll try to at least give a flavor of what these kinds of conditions mean. And the last condition is a dimension condition. So a certain dimension bound is achieved. So what this means is that, so this last condition, to put it informally, would say the following. So if you would look in the moduli space of Riemann surfaces which satisfy the kind of conditions you get here plus the kind of conditions you get here, you'd get some variety, and then you'd compute its dimension. And if that dimension is sufficiently large, in fact, it has to be larger than the expected dimension most of the time. So if you get some variety which satisfies these two conditions, and it is a little bit bigger than it should have been by expected dimension counts, then it has to be one of these M's. So M is kind of these affine manifolds are in some sense kind of rare occurrences. So they occur when some atypical kind of, if you intersect two manifolds, you expect some dimension, but occasionally they will have a higher dimensional intersection, and this is when some of these M's can occur. So let me try to briefly say what the Jacobian is. So if X is a Riemann surface, then you know that the complex cohomology decomposes into H10 plus H01. These are the homomorphic one forms. And you also have here the integer lattice. So the Jacobian of X is, so you take H10, you take the dual of the homomorphic one forms, and you quotient by the integer lattice, the homology lattice. So if you have gamma, which is a path in h1xz, so you have an integer cycle, you're supposed to get a function on holomorphic 1 forms. So if somebody gives you a holomorphic 1 form, you have to tell them a complex number, and the complex number is just the integral of omega over gamma. So this is kind of a complicated way to say that you take c to the g. This is g is the genus. This space is g-dimensional, and so is this one. This is 2g dimensional. So you have some c to the g, and inside of it you have z to the 2g, which is embedded in some particular way depending on the integrals of holomorphic 1 forms and closed paths. And so this is a complex torus. Also, and in fact, an abelian variety. So from this description, it's not obvious, but there's a way to embed it into some projective space and cut it out there by polynomial equations. OK. So this is what the Jacobian is. And so this is a complex torus. So the condition that it has extra endomorphisms means, so the Riemann surface itself might not have any symmetries. But the Jacobian being a torus, it has a better chance of having some symmetries. And the ring of these symmetries, so if you have two endomorphisms of a torus, you can multiply them. So you get some ring. And so you get a whole bunch of symmetries on the torus that you cannot see on the Riemann surface. And the content of the theorem is that this occurs for these guys. And the torsion condition is related to the following. So you have the following Abel-Jacobi map from, or say from x to the Jacobian of x. So what you do is you fix some point p naught, and then, so here's your Riemann surface. You fix p naught here. So you ask, how do you map p to the Jacobian? What you do is you take you map p to, so you're supposed to give a way to integrate, to assign to holomorphic 1 forms functions. Sorry, to holomorphic 1 forms complex numbers. So you just connect them. So you take gamma. So you take a path gamma from p to p naught, and you take the integral omega goes to, so to each omega you associate a complex number, which is the integral over this path of omega. So what happens if you choose a different path? Well, this gamma 1 and this gamma 2, if you take their difference, it's a closed loop. And so you get something that you quotient out by. So you get this closed torus. And the torsion condition is that these points, the zeros of omega, so if you take p naught to be a zero of omega, then the other zeros of omega have to arrange themselves in some kind of, so this torus has the torsion points. So the torsion points are just the ones that, so this is the torus, kind of caricatured. Oops, these are the, for example, the torsion points are these four. This is the two torsion points. And then you can have n torsion, which are just the 1 over n lattice points. And so the condition is that these points somehow, if you take p naught to be a 0, then these other points in this higher dimensional torus, they have to arrange themselves to lie at these special points. These are the two conditions, plus the dimension count. OK. So this is roughly these are the theorems. And
I'm confused about
yeah.
You said that every orbit is an affine invariant manifold.
Yeah.
So that means that every orbit.
Every orbit closure.
So every point then has extra the Jacobian of every point has extra endomorphisms.
The Jacobian of every point on that orbit closure. If it's not.
Right, but since any point lies on its own.
Yeah.
Closure,
So if.
any point has extra endomorphisms.
Okay. So the nature of these endomorphisms. I didn't specify. So the endomorphisms and the torsion conditions depend on the orbit closure. So if the orbit closure is large, then there are actually no conditions. So for a typical point, then there's no conditions. So the statement is that for each orbit closure, there's a list of conditions, which kind of uniquely characterize it. If it's the entire thing, then there's no conditions. If it's some really small dimensional thing, then it's then it has to be of this type. So maybe
So for a generic point, then the endomorphism ring is Z.
yeah. So for the generic point, yeah, and then there's no torsion condition. So maybe I should also say that Martin Muller showed this showed these conditions hold. Hold when this GL2 plus R orbit is closed. So in what sense closed? In the sense that you have some very large stabilizer, gamma, where gamma is some Fuchsian group. So gamma is some lattice in SL2R. So there's always this scaling, which is a little bit annoying, but basically you get a compact Riemann finite volume. So H mod gamma is a finite volume Riemann surface. So in particular, so an algebraic curve. So in the case when the base is an algebraic variety, or so even if it's non-compact. So maybe the thing I should have emphasized here is that the key difficulty is that this affine manifold is not compact. If you knew that M is compact, then at least the first part, that it's quasi-projective, would be automatic. But the main difficulty is that it's non-compact, but it's non-compact in two different ways. There's the scaling, and the scaling is not important, but it's non-compact in more serious ways when the Riemann surface degenerates. So you always have these degeneracies, and so you have that part at infinity, which you have to deal with. So, okay, so maybe let me try to get at least briefly at Hodge theory. So you know that if you have X as some algebraic variety, then, or compact complex manifold, Kähler manifold, then its cohomology decomposes into the PQ components of, so it has this Hodge decomposition. So now, yeah? So now if you have a family, so now if you have a family of varieties, so the simplest example is curves and Riemann surfaces. So this is the case that we're concerned with. But what you get is the data of a variation of Hodge structure. So there are all sorts of axioms, but what you get really is, you see, you have a vector bundle, which is the cohomology of the fiber. So XB, is, let me just put it here. XB, this is just the fiber above B, little b, and capital B. So you have these cohomology groups, and they form a bundle. And in particular, they decompose. So strictly speaking, to get a variation of Hodge structures, you should take something that's called the primitive cohomology. But if you don't know what this means, then don't worry. And I should say here, polarized family. But just imagine this picture for the current discussion. And inside, you also have this topological piece, which is just the integral cohomology of this variety. So you have two pieces of data. The part that is related to the complex structure, this HPQ decomposition, and you also have this integral lattice. And so this data plus the properties that it satisfies is called the variation of Hodge structures. So, and it has a lot of very pleasant properties. And so when the base B is itself a quasi-projective variety, then the variations of Hodge structures have lots of nice properties. But in our case, when you start with an affine manifold, if you want to prove this theorem, you don't know a priori that it's quasi-projective, so you cannot apply all of these theorems to deduce these properties. So you have to work backwards. You have to establish, so to prove the theorem, so this one, what you need is, so you need to establish these properties for M without knowing that it's a quasi-projective variety. So once you establish these properties, and I haven't told you specifically what these properties are, so those properties, those abstract properties that variations of Hodge structure have, they will imply these things in a way which is mostly just playing a lot with linear algebra. So once you establish these properties, you can deduce that M will have to be itself quasi-projective. So what kind of properties does one look at?
So here you're thinking of X as
the curly X or the
curly X. This is
the family of it's the family of Riemann surfaces. Yeah. So B is kind of equal to M, and curly X is the Riemann surfaces that it parametrizes. Okay. So let me.
You say that if you knew that M was quasi-projective, then the properties of the variation of structure would imply.
So deducing all of these properties could be done using the kind of tools that Teichmuller used, for example. So this is kind of amounts to using some semi-simplicity properties of the variation of Hodge structures. And here you have to deal with mixed Hodge structures. But if you know that M is quasi-projective, then somehow everything kind of works just using those properties. But so I keep calling them those properties. But it's just good analytic properties of the bundles at infinity. This is the kind of things you want to establish. So maybe to kind of give a flavor. Okay, so let me say the following. So typically in algebraic geometry, what you do is you imagine that B is just a punctured disk. So let's say that B is the punctured disk minus 0, and you have your family of Riemann surfaces, and maybe which lives here, and then over the singular fiber, maybe you have some nodal Riemann surface. See, my drawing is not going to be good, but maybe you get some singular Riemann surface, and then you try to analyze how all of that package degenerates at this singular point. Here, because you don't know what is happening at the boundary, you really don't have access to the boundary, what you have to do is you have to study the average kind of asymptotic geometry. So the tool to do this is something called Laptop exponents. So I want to just define them and mention that they are actually the numbers that we saw in the beginning, these growth rates of the leaf on that fixed surface. So the general setup is this. Suppose you have a flow on some base B, and then you have V, some flat vector bundle over B. So here's your base. That doesn't have to be compact. And there's a way to flow in some complicated way. So strictly speaking, yeah. So suppose there's a way to flow. So typically GT will be the diagonal subgroup inside GL2R. So this is the kind of object you would want to study. And so you have this flat vector bundle. So above each point, you have this fiber, and then you can move it around the geodesic, the flow. And so you have a map. So you have a map. Let's call it ATX, which goes, or T little b, from VB to VGTB. So you just have this parallel transport. And the statement, so the theorem, the multiplicative ergodic theorem, tells you that under certain assumptions, some very basic assumptions on this flow and this vector bundle, just some standard things you would want to impose on this, is that there exist, so the singular values, or you can think of, if you forgot what singular values are, this is just a way to attach some numbers for a map from one vector space to another. If it would be the same vector space, this would more or less be the same as the eigenvalues. Not exactly, but they're roughly the same kind of numbers of these matrices, A, T, B. So they're of the form e to the t. So they grow exponentially at some rates, e to the t lambda n. And these numbers are the Lyapunov exponents. So lambda 1 are the Lyapunov exponents. And so by studying what happens in this case, so for a general variation of Hodge structures, in fact, you can study it in a pretty general setting. You can deduce all of these sort of nice properties that I was referring to. And the interest in these Lyapunov exponents is in particular because they give you also information about the flow on the individual surface. So these are the numbers that appeared before. And the sum, the rationality of the sum is this. It's a theorem that really uses the Hodge theory of the picture. So even though these are purely topological quantities, you only needed the topological part, the parallel transport. To study these concepts, you really need to use the kind of analytic part. So I think this is probably a good place to stop. Thanks.
You said at the beginning that that sum was related to a line bundle?
Yeah. Yeah, so the rough formula would be the following. So if the V is decomposes as V01, so it's a weight 1 variation of Hodge structure, meaning something that comes from Riemann surfaces, then the Lyapunov exponents satisfy the following kind of symmetry. This is the symmetries of the eigenvalues of a symplectic matrix. And the sum, and again, so assume that B is the unit tangent bundle of a Riemann surface, S. Then the formula is that these guys, lambda 1 plus lambda g, is the degree of this V10 divided by the Euler characteristic of S. So the degree of the Hodge bundle of V10 divided by the Euler characteristic of the base gives you the sum of these Lyapunov exponents. And this formula has been generalized to some inequalities in the case of higher weight and more general bundles. So there's a separate story there about when does this formula hold, or analogous formulas, when do they hold in higher weight. So that's a separate story, which I wanted to say a few things, but I didn't have the chance. But I'll be happy to tell later.
If you want to find out more, come to Mandarin Walk. We'll leave in a couple minutes from now. Okay, thanks again.